So what we're going to do is, first of all, I wanted us to see a specific example of what it meant to be critical numbers. Okay? So critical numbers. We've got to find those critical numbers. Those would be where f of x, the first derivative, equals 0, or where the first derivative does not exist. DNE does not exist. All right, well, that means we have to differentiate this function. All right, let's check it out. The derivative of this, it's a power function. Something to the 4/5 power. The outer function is something to the 4/5 power. So bring our power down front, reduce our power by 1, and then by the chain rule, it won't affect it this time, but I don't want to forget it in case sometimes it does affect it. Got to multiply by the derivative of the inside, okay, which is still going to be 1, so it's not going to change the answer that much. But we need to do it in case another time it did actually change the answer. So this would be, oh, yeah, that's right. 4/5, 4 over x plus 1 to the 1/5 power times 1. So the derivative of that inside is just times 1. So that's not going to change that very much at all. All right. So what we have to do, what's the 5th root? I mean, what is 1/5? Something to the 1/5 power. Do I recognize that as the 5th root of x plus 1? Okay, something to the 1/5 power would be the 5th root of x plus 1. So, what we got to do is we got to decide two things. When is that first derivative equal to 0? When is the first derivative equal to 0? So in other words, when would this equation hold true? Okay. How do we solve that for x? Let's see. Will this ever be equal to 0? Could this ever be equal to 0? I started with one that was hard. Instead of doing a polynomial one, I did this fourth power. Well, okay, can the denominator be 0? No, it should not be. It would be undefined. So it would be undefined if we were looking at the 5th root. The answer is no, it cannot be 0. So the denominator should not be equal to 0. So the 5 times the 5th root of x plus 1 should not be equal to 0. So the 5th root of x plus 1 should not be equal to 0. So I better make sure that that x plus 1 is not equal to 0. So that says that x better not be equal to a negative 1. Okay, I don't want the denominator to be equal to 0. If I plugged into this first derivative of negative 1, in the denominator I'd have negative 1 plus 1, which would be 0. The 5th root of 0 would still be 0. That would be 5 times 0, which would still be 0 in the denominator. So that would be a problem. Cannot have the denominator equal to 0. Well, is this numerator ever going to be 0? What is the numerator? Yeah. So in other words, the only way for this rational expression to be equal to 0 is if the numerator equals 0. Well, is 4 ever going to be equal to 0? It's not. No. So there is no 4 is not going to be equal to 0. So what I'm trying to say here is that there's no value of x to make the first derivative equal to 0. There's not going to be any horizontal tangents here. But there is a place where the first derivative is undefined at x equals negative 1.
Now, did we have to go out and find that? Because looking at the function itself, figure that out.
Actually, no, it's okay. This is an important question. This is an important point. Here's what James's question was. James was wondering, is the function itself defined at negative 1? Right? Okay, it is actually defined at negative 1. Let me show you why. Okay, here's the original function. The original function, without taking the derivative, is x plus 1 to the 4/5 power. Okay? So another way to write that is the fifth root of x plus 1. This is anytime you have a rational exponent, it's power over index. The fifth root of x plus 1 to the fourth power. So what you're saying is what happens if you plug in negative 1 here, I think, right? Okay. So we've got the fifth root of negative 1 plus 1 to the fourth power. So that would be, well, here we're going to have, this will still be 0. It's true that the radicand is 0, but now it's the fifth root of 0, which is still 0. And 0 to the fourth power is okay. In other words, this is okay because it's not in the denominator. So in other words, the value, the function is evaluated at negative 1. Its value is 0. So in other words, this point, the point negative 1, 0 would be on the graph of f of x. That's true. So it is defined at x, the function itself is defined at negative 1, but it has probably a sharp curve, a little sharp corner there. So the derivative doesn't exist there. The function exists there. The function is defined there, but the derivative does not exist there. Okay? So that...
I'm just wondering if it'll always be like, if in any function, if you can look at it right away and say, okay, well, this gives us 0, then will the derivative not be defined at that point?
Not necessarily. No, not necessarily. No. There are times when the reason why the negative 1's no good in the derivative is because once you took 4/5 minus 1, you reduce the power by 1, that dropped that down to the denominator and put you a 0 on the denominator now when x is equal to negative 1. So we probably, for the derivative function, it's not defined. The original function is still defined at negative 1. Okay? Now, I know, I realize now, too, that I picked a hard one to start with. We found that, what did we find out so far is our goal here was to find the critical numbers of this function. So let's just say, let me go back and at least finish this one here. The only critical number for this function is negative 1. That's a place where the first derivative does not exist at negative 1. Now, the function itself is okay at negative 1, but the first derivative does not exist at negative 1. Let me go show you another one.